Okay, so this is Physical Behavior of Matter, Lesson 6. Tonight's a really short lesson. All we want to understand today is the kinetic molecular theory, collision theory, and Avogadro's law. Let's start with the kinetic molecular theory. The kinetic molecular theory is a model that's used to explain the behavior of gases in terms of their particles. Now, one thing I want to say about this theory is that the kinetic molecular theory was designed on the premise of an ideal gas. And ideal gases, they don't exist. We have real gases. We just use this model to help us understand a gas behavior. So, let's take first a look at the four assumptions of the theory, and then we'll talk about how some of these deviate or are not true for a real gas. First of all, it says the volume of a gas particle is so small that it is negligible in comparison to the volume of the container in which it's confined. So what that means, negligible means really doesn't count. So what they're saying is that the volume of a gas doesn't really count compared to the size container that it's in because it's so small. And we know that gas particles spread out really far. The next assumption is that gas particles do not attract each other, meaning they have no intermolecular forces whatsoever. Again, because they're spread so far out, and gas particles usually have London dispersion forces, which are weak forces to begin with. So they say that they aren't attracted to one another and that they have no intermolecular forces. The next assumption is that gas particle moves in random, constant, straight line, which is not here, motion, which means that if I have a gas particle, it's going to move in this direction till it hits something, then it may bounce off in another direction until it hits something else, and then it may bounce off in another direction, so on and so forth. The last assumption is gas particles are perfectly elastic, meaning that they lose no speed after they collide with one another or with the walls of the container. Now, remember that the kinetic molecular theory, as I said, is a model of an ideal gas. And that model works flawlessly for ideal gases. But an ideal gas is theoretical, meaning it doesn't really exist. Ideal gases don't exist. We only use this concept or model of kinetic molecular theory and ideal gases to predict the behavior of real gases. So the assumptions above are not all true of real gases. The kinetic molecular theory and the gas laws are not 100% accurate with respect to real gases for several reasons. First of all, we know that nonpolar molecules, meaning gases, or diatomic molecules like Brinkelhoff, do have intermolecular forces due to their London dispersion forces. And the larger the atom, the greater the IMFs. So that's one reason why the kinetic molecular theory is not true for real gases. Slow movements are subject to more intermolecular forces. If something's not moving very fast, okay, as in a solid, it's going to have more intermolecular forces. because there's less collisions. Also, small volume containers means what? Well, if I have a small volume container, that means that I'm going to have more collisions. Real gases follow the KMT under certain conditions. First of all, nonpolar molecules, because they usually have low intermolecular forces, because they have LDFs. Low pressure, because if I have low pressure, that means that I have high volume, and that means that my gas molecules are spread very far out. And if they're spread out, they're not going to have very strong intermolecular forces. If I have high temp, again, that means that they are fast moving, which means more collisions, which means that they're going to spread out further. And lastly, small size. So there are two atoms in particular which exhibit the most qualities of an ideal gas, and that is hydrogen, the hydrogen molecule, and helium. And the reason being is because they're very small. Okay, so two things that are really important. This usually comes up on the regions. When do real gases behave most like ideal gases? And it's when there's low pressure and high temperature. The other thing are the examples. You need to know that small molecules will behave most like an ideal gas. And the two conditions that really deviate from the KMT theory for real gases are gases have a volume, and it's saying that according to the kinetic molecular theory that the gas particle is so small that its volume is negligible. So that's the first thing. And the second thing is that gases have intermolecular forces. So we might want to say real gases deviate from the KMT theory because, and then you have these 2 points. Okay, let's talk about collision theory. In order for a reaction to occur, particles must collide with the proper amount of energy. That proper amount of energy, as we will soon learn, is called activation energy. And with proper bond angle and position. So let me bring up another screen to help explain this. Here on the right, okay, you have 2 molecules that do not have the right bond angle, or they may not have enough energy. It says new bonds can form only if the atoms are close enough to share electrons. The collision needs to be violent or energetic enough to break the bonds in the reactant molecules. Some collisions are not successful. These are called ineffective collisions. The molecules simply hit and then bounce off one another. This animation illustrates what happens in an ineffective collision. Reactions usually require effective collisions between reactant molecules to occur. The formation of bonds requires atoms to come close enough together to one another. An effective collision must happen with great enough speed, the proper bond angle, energy and force to break bonds in the colliding molecules. So this animation shows an effective collision between two diatomic molecules. The two product molecules formed fly outwards. Okay, let's talk about Avogadro's law. Gases at the same temperature, pressure, and volume will have the same number of molecules or particles. Notice here that they have the same pressure, same volume, same temperature. It doesn't matter that CO2 is a lot bigger than hydrogen or argon. If they're at the same temperature, pressure, and volume, they'll have the same number of molecules or particles. This is always on the Regents exam. So which one has more particles? More particles. Well, if you were just listening, it would be none. They are all the same because they are at the same temperature, pressure, and volume. I'm going to put P, pressure, volume, temperature. Which one of these will behave most ideally? Which one of those will behave most like an ideal gas? Hopefully you said hydrogen, because I said one of the characteristics of a real gas to behave like an ideal gas is that it must be small. And the third question didn't print. Which one has the most atoms? Remember, okay, atoms, particles, molecules, thingies. That refers to Avogadro's number, 6.02 times 10 to the 23rd. So this is now Avogadro's law. Most atoms, none. They are the same because they have the same temperature, pressure, and volume. Okay, that's it. Very short. Next lesson is going to be the combined gas law, and we're back to math.